Last time we left off with Snell's law, light bending in or out, things appearing bigger or smaller. Let's review what we did previously. Let's do the same example of light streaming out from water into the air. Let's take an angle of 50 degrees. Draw a diagram just like you did before. Theta 1 underwater, trying to leave the water at an angle of 50 degrees. At what angle, theta 2, will light emerge into the air? Find the angle of refraction. Find the angle at which the light will emerge into the air. Don't forget to measure from the normal. Pause the video while you do your calculations and check your work, and check your work again. When you've got an answer, one way or another, you can unpause and see what's going on. What on earth is going on here? Why is everybody getting calculator errors? Everyone you text, everyone who's watching the same video is getting nothing but a calculator error. What's going on? Take a look at your most recent calculation, the one that you wrote down just before you picked up your calculator. Your last line says the sine of theta 2, the angle at which light streams out into the air, is 1.0188 and a bit. So theta 2, the angle at which light will leave the water and go into the air, has a sine of 1.0188. What's wrong with this epic math fail? What angle has a sine of 1.0188? There is none. Check the graph, check the unit circle, check every property that a sine wave ever has. No sine can ever be bigger than 1 or smaller than -1. The sine of an angle is the ratio between one of the legs of the right triangle to the hypotenuse. What right triangle has a leg that's bigger than its hypotenuse? At what angle will the light leave the water and come into the air? There is no angle, and that means it won't. Look at the turtle underwater from where we are. Can you see the light reflecting off the surface of the water and never going out into the air at all? That's what this is going to look like. This is called total internal reflection. Total internal reflection defies all our expectations. It's when we shine light at the edge of a transparent surface, in this case, the plastic, and the light doesn't come out. The light goes from the air into the plastic, all well and good, but once it's in the plastic, it doesn't come out again. The light stays trapped in the plastic and has to turn around and go back the other way. Total internal reflection starts with a geometry problem. We all agreed that light coming out of the water or glass or plastic into the air will bend outward, causing things to look bigger. How far out can you bend before you're back in the surface completely? Total internal reflection is the case where in order to leave the water, the light would have to bend outward so far as to be right back in the water where it started again. The light, therefore, doesn't leave the material. One way or another, it's going to stay. We call this total internal reflection. Total reflection occurs right here at the critical angle. Past this critical angle, the light hit the surface, reflects off of it, and goes right back the way it came. By the law of reflection, the angle of incidence equals the angle of reflection. Angle in equals angle out, same as it always has. The critical angle here is the case where total internal reflection first occurs. Quick brain check. Consider the ideas of critical angle and total internal reflection. If light strikes the edge of the glass or plastic at less than the critical angle, what will happen? Think about it. Write it down. Now, if light strikes the edge of the glass or plastic at an angle more than the critical angle, now what's going to happen? Should be something different. Write it down. Unpause the video when you're ready. Check the picture. Less than the critical angle is what we've been doing all along. Light streams out, hits the surface, bends outward to a larger angle. That angle is perfectly kosher, being less than 90 degrees, and off it goes. The light streams into the air and is visible. However, if you're past the critical angle, then there's no possible way that the light could bend outward, that the light could speed up any more than it already is. This will not occur. Total internal reflection will occur and no light will leave the medium. Check this out. This is a zoom in on a fiber optics cable. You can see that the inside of the plastic is not completely uniform. It's got small deformities. It's frosted. You can see the path of the laser pointer inside. Now let that laser pointer go anywhere near the edge. Check it out. Check it out. How cool is that? How cool is that? This is how fiber optics sends data across oceans around the world, data traveling at the speed of light because it is light, data that stays within the cable and has no packet loss, that arrives right out the other end because that's the only way the signal can get out. Jimmy Dan here has set up a laser pointer behind a tube of water that has a hole in it, and you can see the total internal reflection happening right here in the stream of water. Is all of the light undergoing total internal reflection? No. Water has a relatively medium to large critical angle, but you can see here, see the flares, see the flashes of light that actually reach your eyes compared to the light that stays inside the stream of water. Bill the engineering guy has set up an equivalent experiment with a bucket of propylene glycol instead of water when you're looking at the total internal reflection here, because the different index of refraction, you can see the actual bending of the light inside the beam. Is that awesome or what? You can actually see those bends. Now, how would we go about finding the critical angle? First and foremost, check the scenario. Critical angle, total internal reflection, is a problem for getting trapped in the water, in the glass, in the plastic. This is the case of light in something trying to get back out into the air, speeding up, bending out as it exits the glass or the plastic or the water or the oil or the prism on its way back out. Total internal reflection is the case where light gets trapped inside the prism. See? You can't have total internal reflection in the air because nobody gets trapped in the air. The air is when you're out already. So check to make sure you're in the right part of the problem. Is N1, the place you're coming from, greater than N2? If so, you've got the problem set up correctly. If not, you're asking a nonsensical question, or you're reading the problem upside down. What's the first angle at which the light trying to get out suddenly makes a turn and arrives back at its first surface? You can get out at 70 degrees, you can get out at 80 degrees, you can get out at 89.99 degrees, but you can't get out at 90 degrees. 90 degrees is back in already. This is theta 2. Set up Snell's law, N1 sine theta 1 being the critical angle, equals N2 sine theta 2 being 90 degrees back in the surface. Set up your algebra and solve for the critical angle in terms of N1 and N2. Pause the video and resume when you're ready to check your work. Got your critical angle? Theta 1, the angle at which you tried to get out but didn't? If so, you should get an inverse sign just like the ones you've been doing for Snell's law all along of N2 over N1. There's your equation. Put a box around it. Using your nice new equation, find the critical angle going from water into air. Pause, find it. Ooh, 48.8 degrees. That explains why our middle example worked so nicely, but our last one didn't. 50 is greater than the critical angle from water into air. Light won't ever leave the water at 50 degrees because it can't leave the water at anything greater than 48.8. Follow-up question from the previous lecture. We looked at the index of refraction chart and we found out that the greater the index of refraction, the more expensive the material was. See? Why? What is it that we're paying for? Let's check it out. The largest index of refraction known to humankind is diamond, 2.42. What critical angle will this give rise to if light tries to stream out of the diamond into the air? Get your formula all set up, bust out your calculator, check that you're going from the diamond into the air, which is not always possible, as opposed to from the air into the diamond, which is always possible. That's why we call it transparent. Find the critical angle. Pause. Is this a large critical angle or a small critical angle? Compare the 24-ish degrees you're getting now to the almost 50 that you got for water, and consider how many angles from 0 to 90 are bigger than your critical angle. If your critical angle is 50 degrees, then only 40 out of the 90, less than half, are bigger than the critical angle, and less than half of the light will be trapped inside. We saw plenty of light streaming out of the water and into the air, even when the water was so beautifully illuminated by the green laser light. But if your critical angle is only 24 degrees, most of your 90 degrees is going to be taken up with angles that are more than the critical angle, that are going to undergo total internal reflection. If most of the light that goes in has to hit not just one facet, but several on its way out, if the light bounces inside, around and around and around and around the gem, that's what we perceive as sparkly. Gems have crystal lattice that allows them to be cut naturally so that the light is reflected the appropriate number of times, sending it all out sparkling beautifully after an appropriate time in the same direction whence it came.